Knot theory is the mathematical study of knots. It also includes their applications in diverse fields like biology, chemistry, and quantum physics. We'll be diving into the fascinating world of knots and exploring how mathematicians and scientists use them to understand various phenomena. A mathematical knot is defined as a closed loop in three-dimensional space that cannot be untangled without cutting. This definition differs from everyday knots, which have loose ends that you can manipulate. A key point to remember is that, unlike everyday knots, mathematical knots have no loose ends, forming a continuous closed curve. Let's explore some basic knot types. First is the unknot, which is simply a circle. The next one is the trefoil knot. It is the simplest true knot possessing 3 crossings. Finally, we have the figure 8 knot, characterized by having 4 crossings. Knot invariants are properties that remain unchanged under deformation. These are tools that help us distinguish different knots from each other. Examples of knot invariants include the crossing number, the Alexander polynomial, and the Jones polynomial. The Alexander polynomial is represented by delta of t equals determinant of v minus t times v transpose. It is used to distinguish different knot types. Knot theory finds significant applications in biology. One important area is DNA topology, where knot theory helps in understanding DNA supercoiling and replication mechanisms. Another application is in protein folding, where it aids in analyzing knots in protein structures and folding pathways. In chemistry, knot theory plays a role in understanding molecular knots, which are synthetic knotted molecules with unique properties. Additionally, the topology of knots can affect molecular reactivity and selectivity in catalysis. Knot theory has emerged as a valuable tool in quantum physics. In topological quantum computing, anyons and their braiding operations are used for fault-tolerant computation. Additionally, in quantum field theory, Wilson loops and knot invariants play a crucial role in gauge theories. Knot theory matters because it serves as a cross-disciplinary bridge, connecting pure mathematics with practical applications in various scientific fields. It also lays the foundation for future technologies, such as quantum computing and advanced materials. In conclusion, mathematical beauty meets real-world impact through topological insights gained from knot theory. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.